Good morning. This is Module 9. So, the unequal heating of Earth. So, basically, we're going to talk about why the Earth does not get equal amounts of heat throughout the year or throughout the season. And then also climate change a little bit. Um, the Earth does not get equal amounts of energy from the sun, and that's mostly because it's tilted. So the Earth is not straight up and down on its axis. And so when we look at climate change, that's the reason that climate change doesn't affect everywhere all the same. So not everywhere is getting warmer. Some places are actually getting colder. And it's just because of the way that heat rises on Earth, heat settles, and then the Earth is spinning, it's tilted. There's all kinds of factors that play into that. And then also why we have different biomes and ecosystems. So different biomes, meaning that there's different areas like rainforests, deserts, things like that. It all has to do with the unequal heating of Earth's surface. All right, so atmosphere, there are different layers of the atmosphere. And so we will learn those if you didn't learn those in earth science in ninth grade. So we've got troposphere down here. So this is the area that we live in. So we breathe in this, our airplanes fly in this. We never generally leave this unless you are attempting a world record in something, or you're flying a really high altitude jet, or you're an astronaut. So otherwise, you won't leave the troposphere. So this is the troposphere here. And then we have the ozone layer kind of sandwiched at the bottom of the stratosphere. That's really important to know. So know where the ozone is. The ozone becomes very important, especially when we're talking about our biomes and climate change in general, and just the energy from the sun. But the ozone layer is here, and then that is technically in the stratosphere. So ozone layer is not in the troposphere. I know in this picture it's a little bit hard to tell, but it's in the stratosphere, just the lower layers of it. Then you've got the stratosphere, then you've got the mesosphere, then the thermosphere, exosphere, and then you've got technically space beyond that. Just to give you an idea of where all this is, the astronauts are in the mesosphere. So the space station kind of hangs out in this area here. A lot of satellites are in the mesosphere and thermosphere. The stratosphere, we generally don't have anything there, maybe weather balloons, maybe some really low satellites, but generally we don't have much there. All of our climate or our clouds, weather, the highest mountain, Everest, they're all within the troposphere. So they're not anywhere above that. And then this is just showing temperature. So notice how the temperature decreases as you go up in the troposphere, and then you hit this kind of zone here, the ozone layer. And then the temperature rises, and then we get to the mesosphere and the temperature drops. And then it continues to drop a little bit into the thermosphere, but then it rises dramatically. And as we go up with altitude as well. And then, of course, the exosphere, you're out in space. So the reason it does this, we'll talk about. But basically, in the troposphere, as you go up in elevation, you get less and less gas. And so the gas is what traps the heat. Well, if you have less and less, then you're going to have less and less oxygen, less and less heat, all of that. The stratosphere is where we have the ozone. So that's why the levels increase, temperature increases, is because the ozone layer is blocking a lot of harmful UV radiation, but that's also radiation that would cause temperature to rise. So it increases in the stratosphere. And in the mesosphere, there's very, very little gas at all, like almost non-existent. And so temperature drops. The thermosphere, we've got ions interacting with the sun, and that's creating the northern and southern lights. And that's plasma in the sky. And so that creates this temperature rise in the thermosphere. And then exosphere is out in space. So it's either going to be extremely hot if you're in the sun, or extremely cold because there's no atmosphere blocking or absorbing anything. All right. So that kind of brings us to this question: why is it hotter at the equator than at the poles? Well, the equator gets more, the earth is round. The equator gets more direct sunlight than the poles do. Even though in the winter, when you think about like the northern hemisphere, the North Pole gets, there's about a month or so where it gets 24 hours of daylight. No darkness at all. A little bit of dark, kind of like maybe like dusk, darkness, but never really dark. Um, but it stays really cold there. And it has to do with the angle of the sun hitting it. And we'll look at that here in a minute. All right, so let me move my little video. All right, so if we look at this picture, here's the sunlight hitting the earth. So it's direct, you can see it's much shorter path of travel at the equator than it is at the poles. And so also when you think about, it's showing basically the amount of atmosphere it has to go through. So notice how this right here is not much different from here to here. It's not much different than from here to here. But look at the atmosphere. So the little dotted lines, dashed lines, are the sunlight going through the atmosphere. That is a lot different. So there is a lot more atmosphere it has to travel through in order to get to the surface of the earth, especially at the pole. So it's going really far through a lot of atmosphere, and the atmosphere helps to absorb energy. So if it's absorbing energy, then that energy is not getting to the surface of the earth, so therefore it's colder. So it doesn't matter if it's getting 24 hours of daylight or darkness. Well, daylight we're talking about, but it's going to be colder because it's traveling through a lot more atmosphere. And so that is why, and that's this differential heating. And that's actually really important for weather. So without that, Earth would just kind of be the same all the time. But because we have this differential heating, we get areas that are hotter, areas that are colder. We also get different pressure regions. So we get areas that have higher pressure, areas that have lower pressure, and that creates our major weather systems that we'll talk about later. All right, so this term albedo, this is when the sunlight's hitting the earth, you have reflection. And so you guys have experienced this if you've gone out to the lake or you've gone out to the snow and maybe you forget your sunscreen, especially if you go to the snow. You get a really bad sunburn really fast if you're out in like skiing or snowboarding. And the reason is because it's a white color and white reflects light. So you're not only getting the light shining down on you, but you're also getting light shining up. So there's a lot of reflection going on. And so it's also not warming. So sometimes think about like when you go skiing or snowboarding and it's a really hot day and you might have just a t-shirt on and your snow pants and you're sweating. But the snow is not, it's melting. It's getting kind of mushy, but it's not really melting like you think it would. And so that's because it's reflecting. So the energy is not being absorbed. If the snow is black, that would be a different story. But it's not. So it reflects. So albedo is that reflection, and that's pretty important, especially when we talk about environmental things. So what happens if we take a nice green lawn and we pave it with blacktop? What do you think is going to happen? What do you think happens when you go and walk on that in the middle of summer? I would much rather walk on the grass than I would the blacktop. It's going to burn my feet. So why does it do that? Why is it different? Well, think about what's going on. So the grass is not only photosynthesizing, but it's a different color. The pavement is black and it's not doing any photosynthesis. So it is absorbing all that energy. And then same thing with the oceans. You can see these are just percentage of what's happening. So you can see the albedo is what it's showing. So 10 to 60% is what the water is reflecting. Depends on the temperature, or not the temperature, but depends on the color of the water, what's going on in the water. And then the clouds do the same thing. So 10 to 90%. The snow, just a variety of things. So you can see that's quite a bit. So that's quite a bit of reflection. So when the ice caps start to melt and we talk about the ice caps melting, it's kind of important because now we have less albedo. And so if they're melting, then we have more absorption. And that's kind of that negative feedback loop, or positive feedback loop that we experience. And that we talked about in the last chapter. And then we've got grasslands, a variety of things. So notice the asphalt. I talked about that being very dark and absorbing. So we have a lot of energy being absorbed, very little being reflected. All right, and then I talked about the seasons. So Earth's tilt is causing the seasons. That's exactly why we have seasons. And so you can see December versus June. So notice how the northern hemisphere is tipped towards the sun in June and summer in general. And then in winter, it's tipped away. So this would be where we have 24 hours of darkness. This is 25 or 24 hours of light. And then we've got our spring and fall equinox. So the when we have equal day and equal night at the equator. And so this is our whole year going by. Um, so let me move my little picture so you guys can see it, what it says anyways. So this tilt of 23.5 degrees, that's a tilt of the Earth. And that also happens to be this Tropic of Cancer and Tropic of Capricorn lines. And so these are basically the lines where the energy is going to be directly hitting that area. So it's directly hitting, that's as high as it goes in the summer. This is as low as it goes in our winter. It's opposite for the other places.
Imagine that you live in North America, and one day you call up your friend in Australia. You guys are talking, and you make plans to go visit him next summer.
So, anytime next summer works for you?
Yep, whenever's best for you. Surprise me.
In a few months, July rolls around, and you hop on a plane for your Australian vacation. Imagine your surprise when you show up at his house, and he tells you,
"What are you doing here, mate? It's the middle of winter."
And then you say,
"Winter? It's the middle of summer back in America."
And your friend's like,
"I don't know what to tell you. July is winter for us."
Okay, I don't get this. How can it be summer in America and winter in Australia at the same time?
That's a great question. I think we can help you out with that. To answer this question, we have to zoom way back and start with a top-down look at the Earth's orbit around the sun. Oh, by the way, everything you see in this video isn't to the correct scale. Now, the Earth's orbit isn't a perfect circle. It's actually an ellipse. You usually see it drawn like this. Lots of people think,
hey, this must be why we have seasons. When the Earth is close to the sun, we have summer. And when the Earth is far away from the sun, we have winter.
But that's actually not true. If that were true, it would be summer in America and Australia at the same time.
And we know that's not the case.
Exactly. The way we've drawn Earth's orbit here is really exaggerated. People just draw it that way to highlight the extremes. In actuality, there's a relatively small difference between the Earth's closest and furthest points from the sun. If we draw Earth's orbit with the correct shape, it looks like this. You can see it's actually pretty circular, but it's not perfect. So it's not the closeness of the Earth to the sun that causes the seasons. To see what's actually at work, we have to look at the orbit from the side. In our side view, the Earth is revolving around the sun in this orbital plane here. It takes 1 year to go through a full orbit, 365 days. Remember, at the same time, Earth is rotating on its axis once every day. The important thing, for the seasons at least, is that the Earth actually isn't straight up and down. It's tilted at an angle of 23.5 degrees. So, when the Earth is on this side of the sun, the northern hemisphere is angled away from the sun. The southern hemisphere is angled toward the sun. When the Earth is revolving around the sun, it stays tilted in the same position. The axis doesn't wiggle around or anything. It just stays fixed in a certain direction. So when the Earth is over here, the northern hemisphere is angled towards the sun, and the southern hemisphere is angled away. When a hemisphere is angled towards the sun's rays hit it directly. That's what's happening in the northern hemisphere here. But when a hemisphere is angled away from the sun, like the southern hemisphere here, the sun's rays hit it indirectly.
Okay, so what difference does direct or indirect sunlight make?
Oh, there's a huge difference. Let's take a look with a simple experiment. In this experiment, we're going to use a flashlight to simulate the sun. Say that the flashlight is a particular sunbeam. If it's shining directly, all its energy is concentrated in a certain area. But if the sunbeam is shining indirectly, the area is larger. This means that the same amount of energy is spread out over a larger area. So, in a particular point on the paper, it feels colder in the indirect sunbeam than in the direct sunbeam. And the more indirect the sunbeam, the larger the area. It's important to note that the amount of energy in the sunbeam is always the same. It's not changing. However, if it's spread out over a larger area, we feel it less. Let's take a look at what this means for the Earth. Here we have a globe that's angled at about 23.5 degrees. It's June, so the northern hemisphere is angled towards the sun. If we shine the flashlight directly on the northern hemisphere, we see it illuminates a certain area. But when we move the flashlight to shine indirectly on the southern hemisphere, we see that it's illuminating a larger area, just like we talked about. So let's put it all together. When the northern hemisphere is tilted towards the sun, it's receiving direct sunlight. It feels warmer, which means it's summer there. And the southern hemisphere is receiving indirect sunlight, which means it feels cooler. That's winter. 6 months later, when the Earth is on the other side of the sun, we have the opposite. It's the southern hemisphere receiving direct sunlight, so it's summer there. And the northern hemisphere is receiving indirect sunlight, so they're having winter. And now you know the reason for the seasons.
Awesome. So it's not how close the Earth is to the sun that matters, but instead it's the tilt of the Earth.
Which is also why it's winter in Australia at the same time as it's summer in America.
You got it.
Well, I think this has been the most educational vacation I've ever had.
And there's so much more to talk about. Did you know that the Earth...
I actually think I'm good for now.
Oh, okay.
So, what'd you like to do now? We can go bushwalking and Barbie and get some tucker.
All right, and that is it for Module 9. And so hopefully you enjoyed, and I'll see you back on Module 10.